Okay, do you remember the paired t-test? So the paired t-test was something that we would have done a few videos back, and it's a situation where maybe you've got a treatment group and you want to compare the pre-test with the post-test, or maybe you collect samples from two different instruments at the same time, and you want to compare whether or not the two instruments are performing differently or performing similarly. So with the paired t-test, we usually assume that the data are normally distributed. But what do you do when the data from your two groups that you're comparing are not normally distributed? So again, we can fall back on a nonparametric equivalent. And in the case of this presentation, I know of two nonparametric equivalents that seem to be the most common standards used, and they have their strengths and their appropriate times to be used. So I wouldn't necessarily recommend using these unless you know your data are in fact not normally distributed, because otherwise these methods are not commonly used. All right, so this is the paired t-test equivalent. So in Stata, we can use the Wilcoxon signed rank test, and it's got a short name of just signed rank if you're entering it in as a command. It assumes a similar shape distribution, so that the histogram with the little curve in it, it assumes that the two things you're comparing have a similar shape with regards to the histogram. And you'll also occasionally see researchers use something instead of the signed rank test. They'll actually use what's called the sign test, and this is a more simpler design, and it doesn't really care about whether or not the distributions have the same shape or not. So if you're comparing two things that have different shape distributions, both not normal or one of them not normal, if the distributions are not the same shape, then a sign test would be more appropriate. However, the sign test is not viewed as powerful of a test or as robust of a test as something I've heard as the signed rank test. All right, so I'm going to give you a practical example. Uh, Last year, I had been using this Blue Water Biosciences Coley plate overseas a lot because it doesn't, for measuring E. coli in people's drinking water, because it doesn't require an incubator. It already has the food for the bacteria in the plate. So you just pour the water on the plate, and then when you have a black light, you can shine it over it and count the ones that are glowing blue, and that will tell you that those are E. coli positive wells. And then you match up the number of wells with some sheet that the company provides you, and it tells you how many. So like this plate's got 2,424 E. coli on it. Now it's 96 wells were all glowing, and then when you match up 96 wells with their table, it tells you that that's more than 2,424 E. coli per 100 milliliters. It's a lot. We wouldn't swim in water with more than 235 in the United States, and these are examples of like people's drinking water. Another one that's been out there on the market for a while is this thing called IDEX CoAlert, but it requires a sealer and an incubator and buying these custom products from them. And it works really nice, but you do need the electric for the sealer and all of that. The standard method is this method called EPA method 1603, where you filter the water and the E. coli and other bacteria get captured on this filter, but you put the filter on some food, and the food is very selective for what's able to grow there, and the E. coli that grow there will then take on a purple color, making them very easy to see. So you might be interested in comparing, I know I was interested in comparing whether or not these Blue Water Bioscience results actually match up with the EPA method 1603, because if they do consistently over and over again, now there's some other ways of doing this than what I'm going to approach it with. We're going to talk about correlations in a future presentation, but if you're wanting to see whether or not there was a difference between individual samples, as it relates to comparing the Blue Water Biosciences Coley plate versus this method or versus the IDEX method, you might be interested in comparing the means or comparing the medians or comparing the ranks or something like that. So it all depends on how the data are looking with regards to their distribution. So let's say we want to compare the Blue Water Biosciences Coley plate versus EPA method 1603 going forward. So if we want to compare the three methods to see if they are the same as the EPA method, or the two methods to see if they're the same as the EPA method, we could compare them two at a time. Now the results were recorded for E. coli in colony forming units or most probable number per 100 milliliters. We'll treat those as the same. Number of E. coli per 100 milliliters of water. And we also have reason to believe that our data are not normally distributed. So the t-test in this case should not be used unless we transform the data, or we should just use the nonparametric method. So the t-test again should not be used with the data as they are currently. There's something we can do later called log transforming, but we'll talk about that next time. So the one option we've got left other than log transforming would be to do a nonparametric equivalent test to the two sample paired t-test, or the paired t-test. So what's the options? Well, first let's just verify that our data are normal or not. So in this case we do the Shapiro-Wilk test, and in Stata it can do three things at once. We're interested in Coley plate, that's the plastic well one, versus EPA method 1603. But we can see that when we do this in Stata, the Shapiro-Wilk test, all of them have extremely low p-values. So our data are definitely significantly different from the normal distribution. Now, the next thing, do you remember? The sign test and then the matched paired signed rank test should be used differently depending upon the shape of the distribution. So way back we had this command histogram, Coley plate, and then we didn't use the word normal here after a comma. We just did the histogram, which just gives us the bar charts. But when we put this comma normal, it'll actually plot its best normal curve for us. So let's see what happens when we do that to see if these things have a similar shape. So obviously when we look at the histogram for our Coley plate, we see that the histogram clearly has a big skew in it. So we have this huge right tail. These data are not normal. And then when we have the comma normal, here's the best fit normal curve. Let's see how that compares with Coley-Lurt. Looks very similar. And then how does that histogram look compared to the EPA method? Again, very similar, except for we got some higher numbers out here. So the test, or the question of whether or not there's a similar shape or not, I'm sure there's a statistical test that could be done to do that, but visually, if you say yes, that these all look the same, if you say yes, then we can use the more powerful test, the Wilcoxon signed rank test, which in Stata is just rank sum Coley plate equals EPA method. If no, then we can use the sign test, which is just in Stata, sign rank Coley plate equals EPA method. So very simple commands. If you want to use point and click methods, at the very top of Stata, up about right here on your Stata window, you'll come to statistics, summaries, tables, and tests, nonparametric test, and then you've got three options down here that may be of interest. The first one is the Wilcoxon matched pairs side rank test. So that's the one that's the most powerful paired t-test equivalent. This is the one that assumes that the distributions look similar. The next one is this test of equality of matched pairs, and this is the more simplistic one called the sign test. It's less powerful, but does not care whether or not the distributions have a similar shape. Notice both of these are matched. These are the equivalents that we have to the paired t-test for comparing matched observations, pre and post testing, or an observation about air quality from 1 meter at a certain time on a certain day versus air quality from a different meter at a certain time on a certain day. These are our equivalents here, these matched ones to the paired t-test. And then we've done this one already, the Wilcoxon-Rank sum test. That was the test that we did for the group comparison. When we compare the overall kind of group, the final numbers for the whole group, it doesn't really care whether they're paired or not. So the best ones for comparing paired or matched data are these two, and again, the match sign rank test is the best one to use, but it assumes that the shape of the distribution of group A versus group B are the same. So using Stata, rather than these pushing and clicking on these buttons, and the buttons after this are also confusing, it's just easier to just type in sign rank Coley plate, saying that we're doing the sign rank test and we want to test whether Coley plate is equal to EPA method. And that's assuming that the distributions are of similar shape. And they look pretty similar to me. If you don't think the distributions were a similar shape, you can do the sign test. And again, it's a very simple command. So look at the Coley plate histogram, look at the EPA method histogram. They kind of look similar. I mean, these bars are a little higher. This goes way out to like 8,000. This one goes up to like 2,000. So you could argue that one's better than the other. Again, I'm sure there's a stat method for it, but it's a bit more advanced for a basic biostats class. So when we do the more powerful test, the sign rank Coley plate equals EPA method, when we do that test, saying that these are providing similar results, the distributions are similar and they're providing similar results, saying that Coley plate is equal to EPA method, we got a p-value down here of 0.0998. So is there a statistically significant difference? Well, usually alpha is set at 0.05. So since 0.0998 is higher than 0.05, we would say there's no statistically significant difference. So there's no difference between group A and group B, or in this case, Coley plate and EPA method. These are statistically similar, but it's getting close, so they're almost different. But based on the signed rank test, no statistically significant difference. If you think that they actually look different with regards to these shapes, and you think that the distributions are different in shape, then you can use the sign test. So that's the signed rank test, the sign test. And the sign test, Coley plate equals EPA method, gives us these one-tailed tests, saying that one's higher than the other. So is the median of Coley plate higher than the median of EPA method or whatever. But we are going to just look at the two-sided test. Is there a statistically significant difference, yes or no? And what do we see for the p-value? We see a p-value of 0.2682. Since 0.2682 is higher than 0.05, we have insufficient evidence to conclude that there is a significant difference between Coley plate and the EPA method. So we would conclude that the results are statistically similar because they're not statistically different. So 0.26 is higher than 0.05, no statistically significant difference between Coley plate and EPA method. That confirms the same results here, just the p-values are different, but they did come to the same conclusion. Now, if all that was a headache for you because non-parametric statistics are confusing to you or they have a lot of weird names that you've not heard of, you can also straighten out our data. Now, how do we do that? Well, stay tuned for how to make your not normally distributed data actually meet the normal assumptions sometimes. So sometimes we can actually transform the data to make it meet the normal assumption. And if we do that, then we can do t-testing and do that paired t-test or even a group t-test if that's what's warranted. So how to straighten out our data and transform it is up next. Thank you.